Hello everyone, welcome back to another video of Marine Maths. So, I made this video because I think it's worth it to talk about something that, I found in regards to friction, right? So static friction. An interesting relationship between friction, right? Friction coefficients. So in other words, like mu s, mu s, stands for the static friction coefficient, and the mu k is for kinetic. So kinetic friction, and the difference between these two is that over here there's no slip-in, right? When you have static friction, there is no right. There's no rub-in between the two surfaces in the points of contact. But then for kinetic friction, of course, there is slip-in. So yes, there's slip-in, and so generally when we try to find, right, the coefficient of friction, so when we try to find the coefficient of friction, for example, for a box, right? A box that's on an inclined plane, then let's say that we can change the angle theta, right, around. But let's say that theta is constant, right? So theta is a constant. And then in the box, of course, everything that's left for us to change is pretty much the material, right? So the material for the box is the one that's going to change. So in this case, let's say that we want to find a minimum coefficient of static friction, right? What's the minimum equal to in order for the box to, start slipping? And the interesting thing about this is that even though the box, right, is going to have a force of friction in this direction, right, at all times before it starts slipping, which is static friction, the box is not going to rotate, right? It's not going to roll because it's just a box. Boxes, generally don't roll, right? Unless, of course, there is an imbalance in the weight. If there is let's say too much weight over here, then sure it's going to tip over and it's going to start rotating, but it's not a uniform rotation, right? So yeah. Now let's talk about objects that actually rotate. So like an actual ball, right? When you have a ball, so a ball like this, let's say, and let's say for the sake of simplicity, that this ball is uniform. It's uniform, right? Constant density, all of that cool stuff. It has uniform mass distribution. It has it's a very nice object, and it's going to have a force of friction in this direction, right? If we assume that there is friction between the surface, the inclined plane, and the ball, there is some friction over here. There is going to be, of course, force of gravity going down, and there is a normal force pointing perpendicular to the surface, right, on which it's rotating. Okay, so these are pretty much all the forces, right? Assuming that there is no air friction, nothing like that. And then, let's say that we want to find, right, what's the minimum coefficient of static friction, right? What's the minimum coefficient needed before the ball starts slipping? Well, in order to do that, right, we'll need to do some Newton's second law, right, stuff. So first we have to define a reference frame. So we have to say that this is our reference frame, usually the best reference frame for this type of problem. X direction, positive X direction goes over here. Positive Y direction goes over here. So here the X direction is really the one that matters most. Y direction, it's really not that important because there's no motion, right, in the Y direction. So then you split off this into its components, Y and X component, right, according to our reference frame. So this is the only force that has two different components, right? Force of gravity has a Y component over here, and it has the X component over here. Of course, doing some geometry, you will find out that the angle over here is theta. So then based on this, we can write out some equations, a couple of equations for Newton's second law. You can say that normal force minus the gravitational force in the Y direction, right, is going to be equal to 0. And why is that? Because, right, in the Y direction, there's no motion. It's no motion. So then we can do the same thing for the X direction. We see that there is the force of gravity in the X direction minus force of friction, which equals to the mass of the ball or the object that's rotating times its acceleration. Now, because of course it's going to rotate. But of course we also have to think about the torque, right, that the friction is applying on the ball, because the ball wouldn't rotate otherwise, right, without the torque. So then the torque on the ball, right, is only acted on by friction force times the radius of the ball, right? So let's suppose the radius of the ball is r, and that's equal to the moment of inertia times angular acceleration. So these three equations are pretty much all we need, right, for this to solve for mu, pretty much, because you know that force friction, right, if you want to find the minimum coefficient of static friction, it's going to be less than or equal to the coefficient of static friction times normal force. So over here we have the normal force, right, and we have I guess the friction. We can solve for that, and so when mu s equals force friction divided by normal force, then we can get, right, the minimum. We can get the minimum. So solve for the normal force. That's going to be gravitational force in the Y direction, which is pretty much the total gravitational force times, I think that's the cosine, right? It's adjacent, so it's times the cosine of the angle, theta. Remember, theta here is constant, so we're not really changing theta. And we have the friction force, which equals moment of inertia times alpha over r. Now, assuming that there is no slipping, right? We know that alpha is a over r, linear acceleration, tangential acceleration at this point, right? Tangential acceleration at is going to be, so this is going to be I over r squared. Okay, so now let's suppose that for this example, this object, right, the ball is a uniform solid sphere, right? And for a uniform solid sphere, the moment of inertia is 2/5 times the mass times the radius square. Of course, I'm not going to go to the derivation. I'm not going to derive this moment of inertia unless you want me to. it's just an integral. Okay, so now we substitute that into force of friction equation, and you get 2/5 mr squared a over r squared. Now notice here that the r squared doesn't matter, so the radius doesn't have any effects, right, on the force of friction. Interesting to note. And this is 2/5 ma. Okay. So then you just substitute these two equations, right? Normal force, and you substitute, of course, gravity over here. This is just mg. Substitute those things over here into mu s, and you get mu s equals 2/5 ma, right, over normal force. Okay, so the normal force we found was mg cosine theta. And clearly the mass, right, doesn't matter here. Mass doesn't matter. Okay, so that's interesting. Now, of course, we want to solve everything in terms of constants that are known, not unknown. So we want to get rid of the acceleration. And so in order to get rid of the acceleration, of course, we got to solve over here, right, on this equation over here. So since we know what's the force of friction already, then we know what's Fgx. Right? Fgx is just in the x direction. It's going to be total, right, vector Fg, magnitude vector Fg, times the sine of theta, because it's opposite. And then we're going to put this here. Well, Fg is mg, so mg sine theta minus 2/5 ma, and that's equal to ma. So you add the 2/5 on the other side, okay, add it on the other side to factor out the a, right? Of course, m doesn't matter here, so g sine theta equals to, and then 1 plus 2/5 should be 7/5 a, multiplied by 5/7, a equals 5/7 g sine theta. And this is very interesting, right? The numbers that you're getting out of here, you might think, right? It's, you know, it's just numbers. It's a numerical answer, and it doesn't have any effects or any physical representation. But we'll see that in fact, all of these numbers and the operations that we're doing have a lot to do with the energy of the ball. So when the ball is rolling down, of course, it's going to have kinetic energy and rotational energy and gravitational potential energy, right, depending on the reference frame. Of course, if you say that the reference frame is always moving along with the ball, there's never gravitational potential energy, so that really simplifies everything. Now, so the mu s then is going to be 2/5 times the acceleration, which is 5/7 sine theta, divided by g. Oh, excuse me, there's a g over here as well. So you see they cancel out. Cosine theta. Oh, now look at this. 5 cancels out, and we're only left with 2/7 sine over cosine, which is tangent, right? 2/7 tangent of theta. Now, very interesting result. Don't get me wrong. This is absolutely mind-blowing. Why? Because for the box problem, when the box is not moving at all, right, but there is still some friction, of course, the equation that we use to find force of friction over here is not going to have mass times acceleration, because it's not moving on any direction, and you end up with mu s equals tangent of theta. Coefficient in front of it is 1. So that's very interesting. Now, if you ask me, okay, what's the whole right? What's the physical representation here from these constants? So, what I'm trying to get to, right, is that you can write the coefficient of static friction as a general formula. You can say that this is equal to some ratio, which is a constant, times the tangent of the angle of the inclined plane, right? Suppose that angle is constant, and you're trying to talk about this. Of course, that's going to be a constant too. Everything's a constant in reality, right? As long as you're not changing anything, mu s is constant because this is constant. Now, how to get this r? Well, it turns out, right, that these numbers over here, they have a relationship between the energy of that ball. Now, let's take a look at that. Now, since this is a uniform ball, well, the ball is, of course, is rolling down, right? And when it's rolling down the hill, let's suppose that let's say that we have a reference frame over here that's moving along with the ball's center of mass, and well, this is going to have, kinetic energy total. The total kinetic energy is going to be defined by two quantities: the kinetic energy linear plus the kinetic energy rotational. Right? So, in other words, the total kinetic energy is equal to 1/2 mass times velocity squared plus 1/2 moment of inertia times, I omega square times omega square, which is angular velocity. And this is a very important part, very important relationship here. The question is, what if we find the ratio of the rotational kinetic energy over the total kinetic energy? The ratio of the rotational kinetic energy of the total kinetic energy. We're basically finding how much of the energy, right, is rotational energy. How much, right, as a percent. And this is pretty much 1/2 I omega square over 1/2 mv square plus 1/2 I omega square again. Now, interesting thing is we can factor out the 1/2s over here and they go away. We can also substitute the velocity by r omega, right? Because we're, of course, assuming that we are just at the threshold of going from not slipping, right, to slipping and rotating. But we're assuming that, of course, there's no slipping, right? So then we have, I omega squared over mr squared omega squared plus I omega squared. Of course, the omega squared goes away. And then really what's left here is the moment of inertia, right? The moment of inertia is really what matters in this problem. Mass doesn't matter because moment of inertia has got a mass on it. So when we substitute our moment of inertia, 2/5 mr squared divided by mr's, well, it's going to be I, which is the same thing, right? 2/5 mr squared plus mr squared. Mr squared doesn't matter, right? It just cancels out in the problem. But what matters here is the constant. It's the constant in front of the moment of inertia. So you get 2/5 over 2/5 plus 1. Now, I'll probably generally write it as, something like a constant a over a plus 1, right? I guess that could be a good way to think about it. Right, so, and I guess it's pretty useful, right, to write it like that. But now, you could also write it as some constant a over b plus 1, right? And then because we have to find, right, the common denominator here, so the ratio is 2/5 over, that's going to be 7/5 and you get, of course, 2/7. And so it turns out that, yeah, it's true. Mu s is 2/7 tangent theta. And that's absolutely true. Because we solved it using, of course, the force, right? Force analysis, using Newton's second law. And so we can come to a general formula, right? We can say that if you have, right, a body, right, rotating and rolling down an inclined plane with some angle theta, the minimum coefficient of static friction over here, before it starts to slip, is going to be always, of course, the ratio of the constant in front of moment of inertia, right, divided by that same constant plus 1 times the tangent of the angle theta. And where does A come from? Come from the moment of inertia defined as A mr squared. Right, so this is the general formula for the coefficient of static friction, okay, of any rotating object. Alright, so that's it. It's a very interesting, relationship that we found here. Something I could never thought of. So a student of mine helped me find it. Okay, so I think that's it for now. So thanks for watching, and I'll see you next time.